Excellent. Okay. Hi, everyone. So, well, me and my co-authors, we wrote the paper that Marcus just mentioned in his talk. And generally, I think what we're talking about is maybe a good complement to what you just heard, because we're talking about one specific instantiation of where you would use memory disaggregation. And I want to go into a bunch of details how that will actually look. I won't be able, I don't have multiple screens or anything like this. I won't be able to see like the Slack, but I do have my phone next to me with the Zoom chat. So if you have anything urgent to me, ping me there. Okay, so today's workshop is really kind of on the intersection of serverless and disaggregation. And there's a bunch of interesting research that is happening at that intersection. There's a lot more interesting research that Marcus just talked about squarely in disaggregation. And specifically here, we're talking about memory disaggregation. And when we really talk about, if we look at these papers that have been published so far and kind of the research that has been going on, many of them are actually using RDMA, and especially RDMA over Ethernet, to implement the disaggregation framework. And because of that, we're very familiar with how that looks. So we are very familiar with this kind of message-based or kind of page fault-based interaction that kind of happens on the multi-kilobyte level. We all know kind of the latency of RDMA is a couple dozens of microseconds, typically what you see in practice. And you can go across the whole data center. You can really get large-scale systems here. And now I want to talk a little bit about how these assumptions change when you look at CXL. And specifically in the CXL memory domain, basically we would move, as we heard twice now, from message space to load store access, by which we mean if you have a cache miss, like you do a load to an address that is on CXL address space, and you have a cache miss in your processor, basically that cache miss comes from the CPU to a CXL port, which translates this into a request that is issued to an external memory device, and you then get a data response back, which typically happens at the granularity of one cache line, 64 bytes. And so that also answers maybe some of the Slack questions we saw, like how many operations per second do you expect to see? Well, if you want to get 100 gigabytes per second, basically each operation will be 64 bytes. So that's kind of the scale we're looking at. So I hope from the previous two talks you have a little bit of an idea how easy it is to actually use CXL. You don't have to change your application. You just use memory like normal. Where I think a little bit of the open questions remain, also as we saw before, is kind of the performance, the latency of accesses. So we often hear kind of hundreds of nanoseconds, and the scale that we realistically will see in practice. And of course, that will change over time. But in this talk, what I want to focus on is just like Marcus, predicting the future a little bit. And I'm looking at this from the specific point of view of a cloud provider. What do we expect to have actually in the data center in 3 to 5 years? And that allows me to give specific answers on kind of the latency and the scale of the system. So this talk will really be about CXL yet again, basically the third in a row. Now, if you think about serverless, you might have specific requirements in how you would like your CXL system to look like you would like to define it in a certain way. But the truth of the matter is, still today, serverless is one of many, many cloud services that we run in the same data center. So we have infrastructure as a service, so just VMs that are hosted out. We have containers and hosted databases and all kinds of analytics and machine learning frameworks, and all of them share the same hardware, the same system, which we call the public cloud. And so when we think about how memory disaggregation will really work, the likely scenario from my point of view is that we will build one system that kind of will have to work for all of them. So we will have to build something that works for the public cloud in which we see these mixed and very heterogeneous workloads, and where we have all the workloads each running in their own virtual machines. They're all virtualized. So that's kind of the unit of abstraction that basically we have to deal with, a virtual machine. Now, if we specifically come back to memory, so how is memory actually virtualized today? So we have this gold standard that we try to achieve. Basically, we want to have all the cores and all the memory of a VM on the same NUMA node, and we statically pin all memory. We pre-allocate all the memory so that you don't ever have any page faults, any kind of delays in the hypervisor. So basically, you end up with a system like this. Typically, on a 2022 CPU, you get about an 85 nanosecond latency to access that local memory. You get about 100 to 200 gigabytes per second of bandwidth, and you have a couple hundred gigabytes of local memory as a capacity in your system. And in Azure, we really achieved this for the vast majority, like 97, 98% of VMs actually see this very, very low access latency. I'm telling you this because we'll later come back and compare this kind of as a performance baseline. Okay, so we have these very, very strict goals in order to achieve high performance, but also, as Marcus already indicated, that comes as a challenge. So the first problem is DRAM has gotten really expensive. So that's kind of where we earlier had the conversation, like, why now? That was not the case 5 years ago. The memory cost is growing very significantly every year. It's going to keep growing even further. Right now, it's about half of server cost. So that's kind of a tipping point for us. And the second problem is that's kind of the utilization problem that Marcus also mentioned. We have this problem that we fragment or strand our memory pretty repeatedly. So when we say we strand memory, we mean that we have other resources on that server that we already scheduled to VMs, and we don't have any more resources left. But there's some memory left, and that memory we can't hand out. So if we schedule all the CPU cores, so we schedule all the NIC bandwidth on that server, and there's memory left, that memory is stranded. And in recent years, we've been really pushing how many CPU cores we've been able to schedule to VMs. But as we do this, we've seen more and more memory being stranded. So here on the y-axis, you see the stranded memory fraction as a fraction of cluster capacity. And I'm here looking at hourly snapshots where I looked at a couple of production clusters, and I look at how many CPU cores are currently scheduled and how much memory is stranded. And you can see this broad band, the error bar is at 25 to 75% percentile kind of intervals. You see this broad band as stranded memory basically goes up and up as more CPU cores are scheduled. So anywhere really between 5 to 25% of memory is stranded. And since that's half the server cost, basically that's really inefficient. So how can memory disaggregation help with that? Well, if you look at today that I just showed, basically you have a CPU socket and you have a fixed amount of attached memory. That's where we go today. And where we want to go to is the system below, where we, in addition to local DRAM, we will also have some CXL pooled DRAM. And really, the pool system here is that multiple CPU sockets will basically be able to attach that same pool. And instead of having, like you see in the top, something like 500 gigabytes on that server locally attached, you go down to 250 gigabytes and then have a little bit in the pool that you can claim locally. So the idea here is that you can reassign that pool memory between these CPU sockets. And you heard Marcus and maybe others you may have seen in the CXL standard. There's many different ways how you can really implement a pool, including a cache coherent one. That's not what we're talking about here, because that's too expensive in our estimate right now. So what we expect to do is we actually implement an ownership model where for some time, a CPU basically gets assigned some fraction of that memory pool, let's say a gigabyte, but then without rebooting, without any much ado, a few milliseconds, you can basically reassign that gigabyte to another CPU socket. And that way we can solve stranding and fragmentation. If now one of those CPU sockets runs out of CPU cores and it still holds a little bit of pool DRAM that it's not able to use, it can just return it to the pool and we reassign it to another CPU socket. Now, you might ask, so how effective is that going to be? And so to answer that question, we ran a little trace simulation. And in that trace simulation, we basically track how much less DRAM would we need in order to fulfill the same amount of VM traffic, basically. So without rejecting any VMs in this cluster, how much less DRAM could we buy? So that's the y-axis here. 100% DRAM is where we are today. We have a 2-socket system. And on the x-axis, I'm showing you as we add memory pool across more and more CPU sockets, how much less memory you will actually see in the system. And I'm showing here 3 scenarios that we evaluated. Basically, a certain fraction of memory is going to be in the pool, either 10, 25, or 50% of memory. And as you increase that, you can see basically you can save more memory. We make 2 kind of key observations here. So the first one is from a cost reduction perspective, from a savings perspective, even small pool sizes are extremely useful. You see basically this curve somewhere around 8 to 16 sockets. Really, you get diminishing returns as you go to larger pools. And the second observation we have is that you really have to put a fair amount of memory into the pool. Otherwise, you just don't see many gains. Like, for example, that green line on the top, you can see it just flattens out and doesn't actually get much more improvement, even as you build bigger pools. So you have to really be focused at staying compatible, at really being able to have a fair number of workloads to use that CXL memory. Okay, so we've talked about the savings. And just to say it again, we can save with a 50% pool size, roughly 10, 12% of memory. Now, what about the costs? And to answer that, we have a rough cost model because we've been building a CXL system for a couple of years. We have some idea of what the costs will be, but there's still some factor that we can't easily account for, which is the overhead for the cables that we need, the enclosure. And you see I made a very rough sketch here. That little orange block in the middle is where we expect to have a memory blade, and these blue blades are going to be compute blades that basically connect to that memory blade via cables. Very, very similar as kind of the literature 10, 15 years ago kind of envisioned it. And we need basically to pay for all of that. And so we made this cost model here, where you have these 2 plots, one for putting 25% of memory in the pool, one for putting 50% into the pool. And I added the dashed line to show basically what is kind of the expected limit of how much we can save. And you can see here in many of the scenarios, even like independent of how much infrastructure overhead we really have, the cost benefit is actually positive, which might be obvious to you, but like as a cloud provider, you still have to run that computation. You still have to make sure that at the end of the day, accounting for all the overheads, accounting for the additional power, the additional chips, the additional enclosure, and all of that, we are really actually saving money. However, we also see that there are inflection points in this curve where if you go to larger pool sizes, basically the cost starts to explode. And that now is starting to tell you a little bit of a story, right? We saw in the previous graph, if you have a large pool size, you get diminishing returns. Here we see the cost is going to increase a lot. I think that's also what Marcus said. That's why you will really see a certain size of a pool, somewhere in the 8, 16, 32 range, not the very, very large pool that you could hypothetically build. Okay, so we've talked about cost. Cost is positive, and we have understood that to some degree. But what about performance? So if we really understand CXL latency, we have to, oh, I heard someone speak up. Any questions? No? Okay. So if we want to understand CXL latency, we really have to understand that end-to-end in the whole system for the whole pool. And I mentioned earlier, the way CXL is being accessed is via what is called a CXL port that is integrated in all the new CPUs that are on the market as of this year. And lucky enough, we know the port latency because Debendra, which is a high-level Intel exec, he measured this on an Intel processor and told us it's about 25 nanoseconds at hot eye a few months ago. So we have that as a baseline. And after you traverse the CXL port, that kind of vague picture I have on the right, the DRAM pool, you will have to actually build a pool. And so you will have to, for example, use a switch, and that switch will have basically multiple ports on one side and multiple ports on the other side, and basically like an Ethernet switch allow you to kind of packet-based switching in here. Now, in order to build a switch, at the very least, what you need is 2 CXL ports, and let's assume you're as good as Intel is building those, so that's 25 nanoseconds each. And in the middle, to connect them, you need some arbitration and a network on chip, which we estimate to be 25 nanoseconds approximately. So at the very least, a switch will cost you 75 nanoseconds. And after you traverse the switch, you're on CXL again, and then you come to your CXL device, which again will add some latency. So at a high level, what we see here, and I think Marcus also mentioned this, that switches are somewhat slow, right? They really, really slow you down. So what we've been working on, and many other industry partners with us, is a much lower way of doing a much lower latency way of doing pooling, which is a switchless CXL topology, which we call a multi-headed device, and that has recently been standardized. So the idea is basically to collapse the switch and the CXL device into just one device, so you don't have to cross these CXL ports too frequently. So basically what this will look on the inside is you have CXL coming in on one side and DDR, like the memory accesses from a memory controller, coming out on the other side. And in between, you have some access control. And again, you need a network on chip. So here, I'm roughly giving you an idea of what we estimate those latencies to be. I should also mention, this is kind of a theoretical analysis that we did because we weren't allowed to publish the actual chips that we have from vendors. We are not building them ourselves. But the actual chips you can buy today, especially there's a couple of Chinese manufacturers that already have the ASICs delivered to us. They're a little bit slower, roughly 50 nanoseconds slower than what you see here. But they promise us they will get pretty close to this estimate that we have. So we're not too far off in our numbers here. Now, if you basically now put this together and build a system, so here I'm showing you what happens if you wanted to build an 8-socket pool using this multi-headed device. If you had a just local access, you have the 85 nanoseconds. For this 8-socket pool, you get to 155 nanoseconds approximately. If you want to build a larger pool, as we also discussed in the Slack chat, the problem with CXL is the cables can't go very far. As soon as you go roughly above 30 centimeters, you will need to have an additional device called a retimer that re-strengthens the signal. And if you want to go to 16 sockets, you just can't cram them as closely together. So just by going to 16 sockets, you'll have a little bit more latency. And now you're somewhere in the domain of about 2x the latency of a local access. And if you want to go beyond 16, somewhere 13 to 64 sockets approximately, that's when you have to put in the switch that we talked about earlier. And we try to not use that switch, but it's just there's a limit how many ports you can have on a multi-headed device. And so we will now have to use switches around the 32 to 64 mark. And that now ends up with a 3x latency. And you can imagine if you add another switch and you want to build an even bigger system, then you're in the 4x, 5x latency. So that's kind of the latencies that we will expect to see. And you again see these inflection points around 16 sockets, there's a big jump. And around 64 sockets, there's yet another big jump. Okay, so how will this actually translate into basically latencies from the user point of view? And for that, we performed over 158 workloads. We basically evaluated them in an emulation testbed that Marcus also mentioned earlier. And we have a couple different scenarios. Basically, the blue line is the 8-ported multi-headed device. The red line is the 16-ported multi-headed device. We also have a line here roughly that is even larger, but I'm not showing that just to confuse people. But basically what we see is on the x-axis, we see the slowdown of these applications as they would run on CXL. Basically, the execution time will be longer. And the y-axis is just an empirical CDF, so you can read off basically different percentiles here. And you may remember earlier, in order to get real benefits, we have to put about 25 to 50% of our workloads on CXL. And if we're okay with about a 5% slowdown, which is kind of our thinking right now, then you can see that is feasible with these 2 8 to 16 ported devices. So a 30–40% fraction of workloads being on CXL is doable, but you have to go with the low latency CXL configuration. Okay, and that already brings me to our conclusion. So from our point of view, CXL is very deployable. I mean, we've also been actively contributing to the standard since about 4 to 5 years. We have a paper that describes our full stack implementation. Of course, what I described here was kind of a sketch of the results, but how you actually use this is described in our pond paper, which will appear at ASPLOS. And just to kind of summarize what we think will happen is that the scale is really likely going to be confined to 16 sockets, maybe if you stretch it 32 to 64 sockets. So this kind of sub-rack scale that I think that's very consistent with Marcus's point of view. For the next couple of years, basically, that's what we expect to see. And we expect to see that actually in major clouds for you to use. And with those constraints, now I hope you can start thinking a little bit of what are the implications for serverless? What kind of applications could you build with this system? Like, is it useful to start, for example, having instant remote forks on that scale across 16 sockets or something like that? So I hope that's the discussion for today. I think we have about 5 minutes for questions. Please feel free to ask away, and maybe you can just read them out for me.
First, is there any questions from anyone in the room?
Yep.
Let's see. Oh, you have one? Okay. Here.
Hi, I got a question for the CXL. So here is like a sub-rack scale deployment, and then you need this retimer compared to internet because like Ethernet, because the PCI signal is not like strong enough.
Right.
So what do you envision like CXL deploy? Just like stick with rack scale, or like maybe it can be deployed in over other substrate? Like I know Ethernet is something very prevalent in the data center. Like what do you think about that?
Yeah, I mean, I very, very explicitly kind of took out the research aspect here, right? Like I explicitly said, this is what I think is practical. From a, like a 10-year perspective, looking at the research part, basically we have to come up with kind of killer applications. We have to come up with a motivation that requires us to go to this larger scale. Because the argument of higher utilization, the argument of basically, reducing stranding, and just having cost effects, they diminish at this small scale already. So that's not the argument to go to much larger scale. So if we can deliver as researchers, basically, an application that allows you to go to larger scale, I'm sure we'll find a way to do this, whether it's multiple CXL switches, which I think is the most likely thing to happen, because you don't want to switch between protocols, or whether it is really going to a kind of CXL over Ethernet kind of scenario in the long run. I really don't know that aspect. But right now, we just have to come up with the applications first to kind of build that motivation for people to, deploy it. Does that make sense? Is that interesting?
He says, yeah. And from Marcos, what will you be using CXL memory disaggregation? What are you using it for, or will you be using CXL memory disaggregation at Microsoft?
So whether it eventually will be deployed, we'll have to see. But we are doing the investment right now. We're investing research. We're investing a lot of engineering resources. We're talking to vendors, so we have the ability to deploy it. And then in about a year or two, the decision point will come to actually put it in the data center. And our goal is to really use this for the whole cloud, use this basically underneath VMs everywhere. And the pond paper kind of lays out that vision, how we think VMs can use that. Of course, all the implications that, Marcus, you talked about, like instant VM life migration, that's great. I mean, that's basically a little bit of a bonus for us.
Ja asks, to clarify, why does an RDMA request in a similar scale system, such as RDMA at 64 byte granularity from a machine on the same rack, have higher latency than a CXL request?
Right. So RDMA has two problems. So the first problem is you have to get your application to issue that RDMA request, right? And like you could change that application, but as a cloud provider, we don't own most of the applications. So we want to build something that kind of works just under the hood for most of them. And so if you're in this regime where you can't change the applications, the only way to hook up RDMA is to do page faults, right? And a page fault is basically a microsecond already. So you're suddenly talking about a 10x latency and you haven't even crossed the network yet. The second aspect is Ethernet switches are just slow, right? An Ethernet switch takes a couple of microseconds, even a NIC takes a couple of microseconds, right? So they're just not optimized for latency.
In chat, so I guess I will ask a question. Oh yeah. Do you think that there's space for other kinds of memory technologies within like a CXL stack, maybe like some kind of like hybrid memory setup?
Of course,
type of thing?
Yes, absolutely. Yeah, you may have heard the big announcement, I don't know, like 2-3 months ago, that we are looking at not putting DDR5 in our memory pools. And so is most of the industry. So we are, all of us, looking for alternative media. And what most people are going to do is put DDR4 in there and harvest that from, previously decommissioned servers. So basically the memory in the pool becomes much more sustainable from a carbon perspective. So that's been our focus. But, once you've kind of exhausted all the decommissioned memory, you will very soon want to basically replace it with the actually fundamentally cheaper technology, maybe some flash or some, newer variant that hopefully emerges in the next few years.
Okay. From Sepeher, sorry if I mispronounced your name. Previous RDMA-based disaggregation systems have been built on kernel paging systems, even huge pages and slabs. But CXL-based disaggregation can focus on cache line accesses. They were wondering, with the heterogeneity of memory systems, what would the implications be for the OS memory layer? Would there be moved to any kind of different types of paging?
Yeah, that's interesting. I mean, I don't know about all the different OSs that run on the cloud. There's a lot there, but I can tell you from the hypervisor memory manager, basically we don't want to do memory management. It's too much overhead. It has all the TLB implementation basically pushes us to do 1 GB page granularity management. So since that kind of is already there, I expect guest OSs will probably also continue to move towards larger and larger pages and try to get out of the way. With that said, because CXL has higher latency, you will have to do a little bit more NUMA management under the hood, right? Like how you saw in Meta's TPP paper, that definitely will change how memory managers work today. So I don't know exactly if TPP is the final argument that will be deployed. It was kind of hard to get in the Linux kernel, but eventually I think we'll have a solution that evolves the memory management in the guest OS.
What do you think of deploying CXL coherent mode? It could have real benefits such as speeding up shared data applications. Could it be implemented in the MHD model?
Right.
What's the latency implication?
Yeah, if you look at the CXL3 standard, basically it's a lot of messaging, right? Like if you want to exclusively have access in one CPU, basically the latency implications are huge, especially if you go to multiple hops. So as of right now, I don't think anyone has figured out how to really use it. It's been standardized, but I don't think that means anyone knows how to use it, and neither do I.